Okay, in this video, I'm going to give the solution of 2008 Step 3 Question 2. Let Sk equals this summation right here, where k is a positive integer, so that S1n is equal to this expression right here, which is just 1 plus 2 plus 3 all the way to n. And S2 is equal to this expression right here, which is just 1 plus 2 plus 1 squared plus 2 squared plus 3 squared plus all the way to n squared. So this question, the first question is asking us to considering this expression right here and show this star expression is correct. Okay, so I believe firstly this expression, the part of this expression attract me is that it's related by nominal coefficients, and which reminds us that if we binomially expanded this summation right here, maybe it will give us some results that is useful. So let's try whether this will work. Summation r equals 0 to n. If we binomially expanded it, the r to the k term will be cancelled, and it leaves us k choose 1 r to the k minus 1 plus k choose 2 r to the k minus 2 plus all the way to r choose k k choose k minus 1 r plus k choose k. We should give it a rectangular bracket, and you will notice that if we extract a binomial expression in front of every r to the j term, we will end up with r choose 1, and this summation r from 0 to the n r to the k minus 1 is just sk minus 1. And if we do all the same to the following terms, we will have k choose 2 sk minus 2 plus plus k minus 1 s1 plus summation from r to 0 to n. 1 is just n plus 1, because there are m plus 1 ones contained in the summation r from 0 to n and k choose k. Okay, so this is one way to express summation r from 0 to n r plus 1 to the k minus r to the k. This is one way to express it, and I think if we express it another way, then we will have the equality we want. If we just observe the expression that is given on the top, we will immediately recognize that if this expression, this star expression is true, then the summation from r equals 0 to n r plus 1 to k minus r to the k is equal to m plus 1 to the k. Then the star will be true. Okay, and so all we need to do is just to recognize that this equality is true, which gives us the correct star formula. And how is that n will be true? So let's simplify the left-hand side a little bit. Summation from r to 0 to the n, from r equals 0 to n, r plus 1 to the k minus summation r from 0 to n, r to the k. And this expression equals apparently the following expression right here is just sk. But what about the previous expression in front of sk? So if we separate the expression into two things, I don't know what I should call it, you will see that this actually equals sk plus m plus 1 to the k. The reason is just to separate n into n minus 1 and n, sigma n minus 1 and n, and you will have the result right here. And by eliminating sk, we will have m plus 1 to the k, in which actually meets our condition. And by equating by equating 1 and 2, we will have the star relation right here, which I'm not actually willing to write it down because it's too long and too messy. So after having this relation, we will the next thing we want to do is just obtain the simplified expressions for S3 and S4, which is just very easy as well, because all you need to do is just to set k equals 4 and it gives you S3, and k equals 5, which gives you S4 again, and which is very long and messy again. So I'm actually not willing to write it down. You may want to try if you want, but it's just a bunch of very easy calculations that everyone knows how to do, but it's just very long and messy and very time consuming. Okay. The second question asks us to explain using this star right here. Oh, okay. Maybe before that, I will just give the result I have from S3 and S4. So S3 is actually equal to, from the answer, 1/4 n to the 4th plus 2n to the 3 plus n squared, and S4 equals 1/30 6 times n to the 5 plus 15 times n to the 4 plus 10 times n to the 3 minus n. Okay, so this is the answer for the first question, and for the second question we are asked to explain using this star formula why sk is a polynomial of degree k plus 1 in n. Okay, so first thing we want to do is to give a clear expression of sk to the n by using this star formula right here. So the first thing we need to do is just to send all our k to k plus 1, because the highest s we have here is k minus 1, so we need to plus 1 for every k, which gives us sk, and maybe I will skip the n here, sk equals k plus 1, 1 over k plus 1, sorry, times m plus 1 to the k plus 1 minus m minus 1 minus k plus 1, choose to sk minus 1 minus dot 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 minus k plus 1, choose k as 1. This is just the expression for sk if we send all the k's to k plus 1. So by this expression, we immediately see that the highest term is m to the k plus 1. This is the term with the highest degree. And for the following ones, because degree of sk minus 1 is actually less than degree of sk, so sk must be a k plus 1 polynomial. Okay. The second sub-question asks us to show that in this polynomial the constant term is always 0. So this polynomial sk does not contain any constant. So this is not very hard as well, because if you observe S1 and S2, they do not contain any constant from here, right? They do not contain any constant. So if S3 and S2, S1 and S2 does not contain any constant. So if the expression, it's not expression, it should be if the recursive formula for sk does not, this is a terribly written, doesn't contain c, constant term c, then sk has c equals 0. And apparently in sk the constant term is indeed 0, because if you binomially expand this term, it will give you a 1 as a constant term, and additionally there is a minus 1 right here, which cancels out with the 1 appeared in a binomial expression. So apparently sk has c equals 0, which is not very hard. You just need to write down some words to explain your idea and your thoughts for the examiner to know what you are thinking. And the last sub-question asks us to show the sum of all coefficients is 1. And that actually needs some of work from the using mathematical induction. So let's get into induction hypothesis. Oh no. Firstly, I think we should do the base case, but base case is rather simple because S1 is equal to 1 over 2 n times n plus 1. So which show that sum of the coefficients of S1 is just equal to 1 over 2 plus 1 over 2, which is just 1. And the base case is rather simple. And for the inductive hypothesis, we need to assume that 1, 2, all the way to k minus 1 are true. And proof for Sk, which is n equals k circumstance. So when n equals k, the expression Sk is equal to k plus 1, 1 over k plus 1 times m plus 1 to the k plus 1 minus n minus 1 minus k plus 1, choose 2, sk minus 1 minus minus k plus 1, choose k, times s1. Okay, so if we binomially expand the term right here, we will have 1 over k plus 1 times n to the k plus 1 plus k plus 1, choose 2, it's not s, it's k plus 1, choose 2, n to the k plus k plus 1, choose 3, and choose k minus 1, plus all the way to 1 minus n minus 1 minus k plus 1, choose 2, sk minus 1 plus minus k, choose 1, k plus 1, choose k, s1. Okay, so because we have assumed that all the case from n equals 1, n equals 2, blah blah blah, to all the way to n equals k minus 1 are true, so the coefficients of those, maybe I should use another color, of those terms are indeed 1. So if we are actually computing the sum of coefficients is of sk, it's just k plus 1 divided by 1 times 1 plus k plus 1, choose 2, plus k plus 1, choose 3. Maybe I made a little mistake right here. this should be also this should be 1, and this should be 2. Yes, this should be 1, this should be 2. So 1, 2, 3, all the way to k plus 1, choose k plus 1 minus 1, the coefficient of this term is minus 1, minus k plus 1, choose 2, minus minus k plus 1, choose k. By eliminating all the binomial coefficients right here, which is from here to here, with here to here, and the minus 1 term are cancelled right here, which actually left us with 1 over k plus 1 times the binomial coefficient of k plus 1, choose 1, which is just 1. And it proves it actually proves the statement right here. This is the okay. So this is the this is the end of this video.